On to part 3 of the twin paradox, and in this part we're going to do a quantitative analysis of what's going on, Bob's perspective versus Alice's perspective. Before we get to that, though, want to go over one more point here that I didn't emphasize probably quite enough in the earlier video clips, because some of you may still be thinking, well, it still seems symmetrical to me. In other words, Alice travels to the star and back again. That's from Bob's perspective. From Alice's perspective, she sees the star come to her, Bob go the other direction, turn around, as it were, and come back to him. How do you tell the difference between those two situations? Aren't her observations the same? Shouldn't they be the same as Bob's observations? In actual fact, this is where the acceleration does come in, and that is only Alice undergoes acceleration. In other words, when you accelerate, you actually feel something, unlike constant velocity motion. So when she gets to the star and she has to decelerate, she'll feel that deceleration. Same thing accelerating back toward Bob. Whereas Bob does not undergo any acceleration or deceleration, does not feel anything. In fact, only Bob, between the two of them, can, where you can have a diagram where he has the same reference frame. He does not change his reference frame at all because he's stationary, as it were, whereas Alice does change her reference frame, as we've seen. So that's where the asymmetry comes in. And certainly acceleration is involved there and deceleration, but what we've argued is that by confining it just a very small region, the effect is such that we can still do the analysis using the special theory of relativity, as we'll see right here, and as we saw in the last video clip with the diagrams. But it certainly is true that the acceleration and deceleration is what makes Bob's situation asymmetrical, different from Alice's situation. Okay, so let's see if we can do the quantitative analysis then. It's really using concepts that we've used a number of times before: time dilation, length contraction, leading clock's lag. The three big ones there are the relativity of simultaneity of synchronized clocks. So let's see how we put this together. And Bob's analysis is pretty straightforward, as we've said before. He observes Alice travel to the star at constant velocity. The star, in his frame of reference, is 3 light years away. She's traveling at 0.6 times the speed of light. And again, we're using units such that c is 1 light year per year. And 3 divided by 0.6 is just 5 years then. Okay? And then he observes Alice's clocks. Alice is moving at velocity v with respect to him. So this is the outbound trip to the star. Ticking more slowly because it's a moving clock, time dilation. And so 1 over gamma factor, gamma being 1.25 for velocity 0.6 c. So 5 divided by 1.25 is 4 years. So he will see her clocks tick off 4 years, while his clocks tick off 5 years for the outbound trip. And then she turns around and comes right back again. So he sees the same thing happen on the inbound trip. She covers 3 light years. It takes her 5 years at 0.6 c. Her clocks tick off another 4 years. His clocks tick off 5 years. And when she gets back, he says, hey, you're only 8 years older than you were when you left, and I've aged 10 years in this case. So again, just using the concepts of time dilation there, it makes sense that Alice would be younger. The hard part again comes on, what about Alice in terms of her analysis? What does she think? Well, so let's think about this a minute. Alice, in her frame of reference, stationary. She's going to see the star coming toward her and Bob receding backwards in the distance. And remember, that means there's a length contraction effect. So in Bob's frame of reference, it's 3 light years to the star. In her frame of reference, okay, so distance to the star, or really we should say the distance the star travels to get to her, right, from her frame of reference, her perspective, is going to be 3 light years over gamma. 3 light years divided by gamma, which is 1.25, and 3 light. I had 3.1 there. 3 light years divided by 1.25. When you do that, you get 2.4 light years. Ly for light years there. Okay. Now she sees the star coming toward her at 0.6 times the speed of light, so 2.4 light years divided by 0.6 c, and again, c, 1 light year per year. When you do 2.4 divided by 0.6, you get 4 years. Okay, so that's how much time ticks off her clock. And again, it's consistent with Bob's observation, although his analysis of how he gets that 4 years is different. He sees his clocks tick off 5 years while she travels, a distance of 3 light years. And he sees time dilation, observes her clocks being time dilated, so it's 4 years. Whereas she sees the distance of the star coming toward her contracted to 2.4 light years, a shorter distance. And at that velocity, it takes 4 years for the star to reach her. So both of them agree Alice's clocks tick off 4 years, or really Alice's clock in her spaceship ticks off 4 years from the time she leaves until the star gets to the star, or the star gets to her from her perspective. Okay, now what about her observation of Bob's clocks? Okay, so she observes Bob's. Now we have to be careful here, because really Bob has at least 2 clocks involved that we're going to be interested in. There's going to be a clock at the star and the clock back on, we'll say, his home planet, if he's on a planet here on Earth, say. And so got one here, one there. They're both synchronized in his frame of reference. They're part of his lattice of clocks. And so in general, though, she will, wherever they are in his lattice of clocks, when Alice observes one of his clocks, she will observe the clock ticking more slowly than hers. Okay? So she observes Bob's clocks to essentially read, well, instead of saying read, let's say I'll just say to tick how many years are they going to tick? Well, again, it's the gamma factor. Her clocks tick for 4 years. So it's 4 over gamma. She sees the time dilation in his clocks. And when you do that, you get 4 divided by 1.25 is 3.2 years. Okay, and again, here's where the paradox comes in, because Alice says, okay, on my outbound trip, my clock definitely ticks for 4 years. We both take a photograph there. We both agree. My clock ticks for 4 years. But 3.2 years, I see Bob's clock ticking more slowly than mine by the gamma factor. And yet, wait a minute, what's this 5 here? Bob is saying his clocks actually tick off 5 years, not 3.2 years. We've got to be able to take a photograph at that point and get them to agree. If the clock is, both at the same point in space and take a photograph, they have to agree in terms of their analysis. And the other part of that, too, is if you just say, okay, same thing for the return trip here. Distance, the star moves away. Bob comes back again. 2.4 light years contracted. 0.6 c. 4 years, another 4 years on Alice's clocks. But she observes Bob's clocks to tick more slowly for 3.2 years. And so it would seem like she has 4 years on the outbound trip, another 4 years on her clocks, 8 years. But Bob's clocks, 3.2 plus 3.2, 6.4. And yet Bob's analysis says, no, my clocks tick off 10 years. So how can we understand that? And we showed diagrammatically last time that's an effect of her changing her frame of reference. That when she turns around, she was in a frame of reference with going this way in lines of simultaneity, parallel like this. When she changes that frame of reference, now the lines of simultaneity are different. It's a different frame of reference. And so there's a jump. It's not an instantaneous jump, but the jump occurs during her deceleration and acceleration phase. Bob's clocks tick ahead from 3.2 all the way to 6.8. And so we want to understand that now quantitatively. Last time we did it diagrammatically. We want to understand that quantitatively using some of our old friends here, if they're friends to you, maybe old enemies at this point, but using our special theory of relativity concepts and equations we've developed. So first thing to note here is, again, let's think about Bob's 2 clocks. He's got his Earth clock and he's got his star clock. And Alice can observe both of those. And let's think about this a minute, that Alice is observing on the outbound trip, or really as the star comes toward her, what's happening? Well, if both clocks, when they start off, were at 0, both of their clocks here, as the star comes toward her, we have a leading clock's lag effect. In that case, the leading clock in the star Bob frame of reference compared to Alice is the clock on Bob's planet. Okay? And that means is the star clock here is going to be ahead of the clock back at the planet. So when Alice starts out on her trip, or really when the trip starts and the star starts coming toward her at velocity 0.6 c, what that means is if Bob's clock here is at 0, Alice observes this clock to be ahead of Bob's clock on the planet. Again, leading clocks lag, so I've got two clocks that are moving this direction so compared to Alice. So Bob's clock is going to be the one lagging, and the star clock belonging to Bob's lattice is going to be the one ahead. And remember that leading clock lag factor is dV over c squared, where the d is the distance in the frame of reference, Bob's frame of reference in this case, between him and the star. And so if we just do that, that's going to be 3 light years. And velocity is 0.6 c. And divided by c squared, but remember c squared is 1, c is 1, so c squared is 1 in our units we're using. So we just get 3 times 0.6, and we get 1.8 years. In other words, when Alice starts seeing the star coming toward her from her frame of reference, and both Bob and Alice, when they start off, both their clocks are at 0 at that point, and then star starts coming towards them, Bob goes away. That means Bob's clock, which is reading 0 at that point, the star clock will be 1.8 years ahead of Bob's clock at his planet, his home planet, as it were. Okay, so let's see what that does then. So as Alice gets to the star, really again, as the star gets to Alice, the star clock is now there. Okay, Alice sees Bob's clocks tick off 3.2 years. Right? Running slower than hers, but because the star clock started out 1.8 years ahead compared to the clock here, Bob's clock here, it means Alice sees it start at 1.8 years down there, then as it's coming toward her, tick off another 3.2 years, and what's 3.2 times 1.8? It's 5 years. So when the star clock gets to Alice, she observes Bob's star clock to read 1.8, because it starts out at 1.8 at the beginning of the journey over to Alice, plus another 3.2 years ticked off, and that's 5 years. Okay? And so they agree. Okay? Both of them agree, yes, Bob says, yes, my star clock there, all my clocks are synchronized as far as I'm concerned, and I see Alice travel. It takes her 5 years to get there, therefore my star clock reads 5 years. From Alice's perspective, she sees Bob's clocks, his lattice clocks, tick off 3.2 years, and the star clock starts out 1.8 years ahead of Bob's planet clock as the star starts moving toward her with velocity v equals 0.6 c. And so she gets 5 years too. Alice says, yes, I understand why your clock reads 5 years, but it's not because you think they're synchronized. It's because from my perspective, that clock was already ahead 1.8 years, and then your clocks ran slowly for 3.2 years. But they both agreed. The photographic evidence would say 5 years for that. So now what happens, though, so that's the outbound trip. Now what happens is on the inbound trip, it's really, now we do have a mirror image type of thing, because from Alice's perspective now, okay, so the star came to her, okay, now the star moves away again, and Bob's coming back this way. As soon as that happens, we really have a change in frame of reference, but more particularly from this analysis, we have a change in the leading clock's lag factor, because now the star clock, as it moves away, is the leading clock, okay? And it's Bob's clock coming toward her that is ahead. And it's going to be ahead by this same factor, the 1.8 years, because again, it's 3 light years, Bob's distance between the star and his home planet at 0.6 c, gives us the 1.8. So here's what's going on. Star comes to Alice. She sees Bob's clocks tick off 3.2 years, plus the star clock was already ahead by 1.8 years, and so when the star clock gets to Alice, 5 years. That's what she sees, and of course Bob sees that as well. Then the star clock starts moving away, and Bob starts coming this way. As the star clock starts moving away, it's still 5 years. It can't change. You know, we just looked at it. It was 5 years. So it's going to start moving away again. And here comes Bob's clock now, but this time, as they're moving this way, the star clock is going to lag Bob's home planet clock. And the difference there, again, is this 1.8 years lag time factor between the two as Alice observes it. And therefore, as the whole system moves back again, the star and Bob's home planet back toward Alice, she will again see his clock tick off 3.2 years, because hers tick off 4 years, same analysis as before, sees his clocks tick off 3.2 years, but his home clock coming back now is ahead by 1.8 years. And again, it's the change in frame of reference here. So really what happens is Alice gets to the planet and figures out, okay, 5 years. And so now maybe she's instantaneously at the planet right there. Now everything is synced up. She's actually in Bob's frame of reference. If they're stationary with respect to others, she's stationary for an instant or two at the star before she heads back in. So she says, hey, yeah, star clock is at 5. My clock is at 4. Everything matches up. Then she starts heading back again. Or from her perspective, Bob starts heading toward her. And at that instant, then, Bob's clock coming back is the clock that's ahead of the star clock. And that's where you get this going up here to another 1.8. 5 plus 1.8 gets us to 6.8. Okay, this is a 1.8 leading clock lag factor here. And then another 3.2 years tick off. Okay, so this deceleration, acceleration can be accounted for within the special theory of relativity by the effect it has on leading clock's lag. And essentially that's the change in frame of reference, that as the star comes toward Alice, it's the one that is ahead, because the leading clock is Bob in that case, moving this way, and it's behind. But then when it goes the other direction, all of a sudden, this is the lagging clock, and Bob's clock is the leading clock by that 1.8 years. Put it all together, and we see the numbers work out. In other words, that Bob, his analysis is fairly straightforward. He sees 10 years tick off. Alice has to take into account not only the length contraction effect, and not only the time dilation effect, she sees Bob's clocks running more slowly, but also the leading clock lag effect as she switches frames of reference there. And put it all together, though, and it makes sense. And yes, they've done experiments like this. I've mentioned this before, where they actually took two very precise atomic clocks, took them up on a plane, commercial airliner or the equivalent, 500, 600 miles an hour in terms of the speed, flew them around, and they had to, because of gravitational effects, they had to take into account general theory of relativity effects as well, but they took into account the special theory of relativity effects, and they did show this difference, that the moving clock, the one that traveled on the airplane and came back again, compared to the clock that was at rest, actually aged more slowly. And so one of the things we'll do next week, actually, is look at some of these effects and see how time travel might be possible, or at least a special kind of time travel. So that's the twin paradox, as I mentioned before, the most famous paradox in the special theory of relativity, but really, again, a pseudo-paradox. It seems paradoxical, but within the theory itself, it all is consistent. It works out with the principles we've established before. Okay, the twin paradox now, part 4. I want to do a brief review of where we've been with this. And also, as you can see, we're going to do something with the Lorentz transformation here. If this is going to distract you, I'd suggest pause the video right now, write that down, and then so you can focus on other things we're going to be talking about here, and we'll get to this in a few minutes. But remember, here's the situation in a smaller diagram this time. We had Alice in the rocket going at 0.6 C, gamma factor of 1.25. Bob in the lab frame. And this time we're going to specifically talk about the rocket and lab frame. And as you can see again over the equations here, we've got R and L standing for rocket and lab. Not right and left, but rocket and lab, just to try to keep things straight here, because sometimes we've had Alice moving and sometimes we've had Bob moving in previous analyses and examples. And so sometimes if we just keep using A and B, Alice and Bob, then we forget who's moving and who isn't. It gets even more confusing perhaps. So Alice is moving this time in the rocket frame. We measure things in light years and years, and went out to a star 3 light years away and then traveled back again. So here's what Alice's world line looks like in Bob's frame of reference. So out to 3 light years and then back. So back in the negative direction, leftward direction, and ends up, according to Bob, 10 years later. He observes her, takes 5 years to get to the star. 5 years times 0.6 times the speed of light is 3 light years, and then another 5 years back. So his analysis, remember, was fairly straightforward. He expects he'll see 10 years tick off on his clock, and because of time dilation, the factor, the 1.25, 1 over gamma factor, he sees Alice's clocks tick off 4 years in each case. And then we did the analysis, so that was Bob's analysis via time dilation. We did Alice's analysis where she sees Bob essentially going away and the star coming toward her and then back again. And for that it was a little more complicated. We had to use not only time dilation but length contraction, because she sees the distance to the star not as 3 light years as Bob does, but a contracted distance. So we had to take that into account. And once we did that, we got the correct number of years ticking off on her clock, 4 years. And then, though, the real puzzle was, we also saw that Alice, of course, saw Bob's clocks running more slowly. And the number we got for that was 3.2 years, again, the gamma factor. 4 years on Alice's clocks. She sees Bob's clocks ticking more slowly compared to her lattice of clocks she compared it to, by a factor of 1.25, which would leave 3.2 years. So why doesn't Alice see Bob only age 6.4 years? And remember, the key was that when we analyze the turnaround here, essentially Alice is changing frames of reference. And so her lines of simultaneity were parallel to the green dashed line that slopes down like this. And when she changes frames of reference, then her lines of simultaneity are parallel this way. And at that turnaround, there's a jump that takes place between frames of reference, and therefore Bob's clocks speed up compared to Alice's clocks at that point and tick faster, as it were. You can actually delve into the details of that turnaround and analyze it and show in more detail, if you want, that actually occurs. But for our purposes, we just say, hey, change it in frame of reference. Therefore, we can see on our diagrams that we did that we get this jump in time from 3.2 years up to 6.8 years. And then during the second leg of the trip, again, Bob's clocks, as far as Alice observes, tick off 3.2 years. Add it all together and you get 10 years. So both of them come up with the same answers, although by different reasoning with that. Another thing just to mention here, and that is because some of you are probably still thinking, well, it just seems that aren't they symmetrical? In other words, Bob watches Alice go away and come back in. Alice in her spaceship, from her frame of reference, watches Bob go that way, the star come this way, and then back again. Just think about it. It seems very symmetrical. But we made the point that only Alice has the acceleration involved. And Bob actually does not feel any acceleration. We mentioned, of course, like if you're in a car that's accelerating, you can feel it being pushed back in the seat or decelerating. You're thrown forward a little bit, or even moving side to side around a curve. Another, maybe more physics way of doing that is to do a simple experiment. Drop a ball. And if you're moving at constant velocity motion, and there's no wind or anything like that, if you drop a ball, it will drop right down at your feet. Because the ball participates, again, we're talking about slower speeds here. We obviously did the analysis with relativistic speeds, but the ball participates in the motion of the object as you're moving. If you're accelerating, however, what happens is the ball falls behind you for a large enough acceleration. For a smaller acceleration, it actually does, but you just can't notice it as much. And so essentially what happens is as you drop it, the ball has the velocity at that point, so it will be going forward with you, but you sort of accelerate it out from underneath it, and therefore it falls behind you. Or if you decelerate, it falls ahead of you because it still has that initial velocity. You've slowed down now, and so it moves ahead of you. So Bob could do that dropping ball experiment all he wants, and during this whole time, it would just fall at his feet. He would not undergo acceleration, whereas Alice would when she was at the turnaround point, decelerating and accelerating. So if that helps a little bit to see what's going on, that even though it seems symmetrical, it actually is not. And of course, the acceleration or deceleration, acceleration at the turnaround point is the key factor because that's what changes the frames of reference for Alice. And then you get the jump going on there, the jump in time as Alice observes Bob's clock. So in one sense, we've talked about how special theory of relativity is all about inertial frames of reference, only applies to that, not in cases of acceleration and deceleration. But you really don't need, say, the general theory of relativity here, which deals with acceleration and deceleration, because you just assume the acceleration and deceleration occurs over a short enough time that you can essentially analyze it using the special theory. And it's really the change in reference frame, which is covered by the special theory, that gives us the results here. So yes, acceleration, deceleration is involved, but we can analyze the results and get the correct results using the special theory. So all that being said, what about the Lorentz transformation here? What we want to show is that you can get the same numbers using the Lorentz transformation, perhaps a little faster as well. The downside is, first of all, you've got to use the correct formulas, of course, the correct versions of the formulas, so you've got to be careful about that. But the downside is you don't get as much feel for what's going on as you do when you break it down via time dilation, length contraction, and leading clock's lag, the relativity of simultaneity. But do want to show that you can do this. Again, our basic equation that we suggested you memorize, if you're in the mood for that and want to use this a lot, is this one here, where we have the rocket moving away in a positive x direction, L for lab. And one way to memorize remember whether it's a plus or minus here is just think about, okay, the rocket's moving away from me if I'm in the lab. That means any rocket value for x will be a bigger value for me because it's moved away. And so if they measure something 10 meters ahead of them, that's going to be maybe 30 meters for me if they've moved 20 meters in that time. So if you can remember that basic situation, rocket moving away, it's going to be a plus sign here in the basic forms of the equation. Then from that, you can derive pretty easily, just in your head, that the other forms of the equation here. So let's start, though, over here with A, calculating Alice's results using Bob's values. And so Bob's values are the lab frame values. And to Alice here, Bob is moving in the negative x direction to the left. And that's why we've got minus signs in these versions. But otherwise, Bob's values, the reason it's nice to start off with that, is Bob's values are pretty obvious what's going on here. So on the outbound trip, Bob's value right here is x. We'll just put this in. So we'll say xl equals 3 light years, right there. And then the time is 5 years. TL equals 5 years. And so that's for the outbound trip. So the question is, okay, those are Bob's measurements right there. What are the measurements x and t for Alice in the rocket at that point? And if you plug the numbers in here, gamma is 1.25, plug these values in for xl and tl. V is 0.6 c. We're using c equals 1 because we're doing light years per year for c. Plug that all in, and you'll find you get 0 for here, and you get 4 for that. And think a minute, does that make sense? Well, yes, because this is Alice's world line, right? She, in her frame of reference, hasn't moved. She's at 0 in her frame of reference. And her clocks tick off 4 years, and that's what we got before. So, yes, that does make sense there. Now, we'll get to the inbound trip in a minute. That's a little trickier. Let's do the outbound trip for Bob's results using Alice's values. Okay, well, we could either do Alice's analysis as we did with the length contraction time dilation, or even just use these results here. We know that Alice here is going to be XR at the turnaround point there, at the planet or star, XR equals 0, TR equals 4. And you plug those values in, and you get, as you should, 3 and 5. In other words, Bob's measurement of that space-time point is XL equals 3, XL equals 3 light years, and time 5 years there. So that checks out, as it should. Now, what about the inbound trip here? We have to be a little careful here because these Lorentz transformation equations apply when the origin is the same for both of them. In other words, when we're starting things at the origin, and at that point, Bob's clocks and measurements are at 0, and same thing for Alice's, then these equations apply. In this case, we're out here. Our starting point is out here at the point 3, 5, and we're going back to the left. So what we have to do to make it easy to use our general equations here is to redefine this as the origin point. And then what happens here is, if you think about it, if this now is our new 0, 0 point, just for the second leg, the inbound leg analysis right there, that means, if we think about it, XL is going to be negative 3. Okay, so this is now 0, count off negative 3 back to here, and so we can write XL equals negative 3 in there. And TL is the same. TL still goes 5, up 5. So it's really negative 3 TL equals 5 years. And if you plug in those values, negative 3 and TL equals 5, just from the diagram here, again, you're going to get XR equals 0 and TR equals 4, another 4 years, as you would expect. So 8 years there. And same thing, inbound trip over here, although in this case we just use XR, again, XR equals 0 and TR equals 4. We've redefined the origin to be 0. So, and again, on the rocket ship for Alice, she's just at 0. She hasn't moved as far as she's concerned. And TR equals 4. And you plug those in. And notice what happens here for this one. Actually, you get XL equals negative 3. Okay? And TL equals 5 again. And so you say, well, wait a minute, XL equals negative 3. Well, remember, again, we've defined this as the origin, so really, as far as Bob is concerned, Alice has moved negative 3 in the negative direction, in the left direction. Okay, and once again, L and R here are not left and right. They stand for lab and rocket. So it just shows us, yes, we can get the same answers using the Lorentz transformation as long as we're careful with our plus and minus signs and think about the origin for the inbound leg there. Let's also, one other way we could do this, just to review a number of things we've done in the past and used for calculations, and that is the invariant interval. So let's just quickly put that up here and see how that works and get the same results, or we should. Okay, so remember the basic form of our invariant interval equation between two space-time points essentially is c squared delta t, and here, well, again, we'll use lab and rocket frame again, so L and R. So we'll just do L squared minus, let's use delta x, just to remind ourselves it's a difference in coordinates, delta xl squared equals c squared delta tr squared minus delta x r squared. And again, what's nice, if we're using everything in light years per year, light seconds per second, then c just becomes 1. So we don't have to worry about the c's there, and we're just looking at the difference in the time coordinates. And so for the outbound trip, for the outbound trip, we have delta XL is 3. Okay, so let's write that down. Delta XL. In other words, it goes to 3 minus 0. So difference is 3 light years. In this case, delta TL, again, we're assuming we've done Bob's analysis. Delta TL is 5 years. for the outbound case. And the other nice thing about sometimes with the invariant interval, if we're doing delta XR for Alice, as we've already mentioned a couple times, that's just 0. Right? Because she stays, from her frame of reference, she's not moving. She's just in her spaceship. And so we can see we have everything we need here. So we've got delta XL and delta T sub L. We have delta XR over here, which is 0, so that disappears. And so we're just left with delta R. And when you do that, plug in the numbers here, we get delta T sub R equals 4. It's easy to verify that if you want. So that's the outbound trip. For the inbound trip, very similar again. So again, you can see here, it's an even easier calculation than the Lorentz transformation if you know the values, and depending on what the situation is, sometimes it's very easy to see what those are. But you lose the insight behind it, and that's why we started off using, first we did our diagrams, the space-time diagrams, and then did our analysis with time dilation and so on and so forth. Now for the inbound, notice what happens here is, as far as Bob is concerned, Alice ends up at 0 and starts at 3. So in this case, delta XL is negative 3. You do the second point minus the first point. 0 minus 3 is negative 3 there. Delta TL, though, equals 5 again. Delta XR is 0 again. And once again, you get really the same thing. You get delta TR equals 4 when you work that out. So that's the invariant interval approach to this. Again, it can be useful in certain cases just to get a quick answer if you need it. One final point here to make or remark, and that is we've mentioned a couple times about experimental results that confirm all this, because no matter how many thought experiments we do like this, there's always the lingering doubt that, is this really real? Does it happen this way? It seems logical once you, starting from Einstein's principles and sort of building on those, and yes, we can see how with a light clock we get time dilation, length contraction, relativity, simultaneity, but because it's so far out of our everyday experience, it's sometimes just hard to know. So I've mentioned, for example, the muon experiment. They've also done experiments with muons in particle accelerators, where they essentially have some muons just at rest, and then other muons circling around them. And from those, they can show that the particles at rest will decay faster than those in motion. So again, it shows the clocks slow down for the ones in motion. So that's well understood and demonstrated. But they've also mentioned these airline experiments they've done. The first one, just if you're interested a little bit in this, it was done in 1971, I believe, where they had 2 accurate atomic clocks on the ground, and then they took some portable ones up in commercial airliners, actually, and flew around. And some flew eastbound, some flew westbound, and they had to take into account a number of things going on, including the rotation of the Earth and the fact that clocks actually run faster at higher altitudes than lower altitudes in a gravitational field like the Earth. In fact, next week we'll talk just a little bit about that to see how time dilation occurs in a gravitational field. So they had to take those things into account, as well as the velocity of the airplanes. And the eastbound and westbound was a little different because Earth was moving, and therefore the clocks on the ground were not completely stationary, but they were moving on the Earth, and so on and so forth with that. So what did they find? Won't give you all the numbers here, but to give you an idea, for the westbound clocks that went on the planes, they had a prediction of that the difference between the clocks and the stationary clocks, stationary in the sense they were still on the ground, was 275 plus or minus 21 nanoseconds. That was the prediction. The result was 273 plus or minus, I think it was about 7 nanoseconds, something like that. So pretty close. The eastbound result wasn't quite as good as that, but this was, they predicted the clocks that flew around would run more slowly than the clocks on the ground by this amount, and the experimental result was very close to it. They actually repeated this in 1996, a form of this experiment where they had, by that time they had better atomic clocks, about 25 years later, and they took one on a jetliner from Washington, D.C. to London and back again, and the prediction there for the result was about 30, almost 40 nanoseconds, I think 39.8 nanoseconds. And the result was about, I think, 39 plus or minus 2 nanoseconds. You don't have to remember these numbers, of course. But the point is they're getting results that are very close to the experimental or the theoretical predictions. And also just the fact that these are very, very small time amounts here. Billionths of a second are what nanoseconds are. They've also done, in the intervening years, since 1996, not that long ago actually, but there's an experiment done in 2010 at the National Institute of Standards and Technology, NIST, which is in Boulder, Colorado in the United States. Other countries have these things, have these institutes as well that are in charge of standards and making very precise measurements and things like that. So in the United States, it's the National Institute of Standards and Technology. It used to be the National Bureau of Standards, but they changed the name a while back. Anyway, 2010, they did an experiment with a very, very accurate form of clock that they had developed. And instead of taking it on a jet airline or anything, they could just do it within the lab at various speeds, even as low as 4 meters per second. Okay, so that's about 12 feet per second, if you're, want to think in those terms, up to maybe about 90 miles an hour. So they did a variety of speeds, but slow speeds. We're not talking about jetliner speeds. And the experimental results matched up nearly perfectly within the very small error bars they had to the predictions of the special theory of relativity. So the theory of relativity is well understood theoretically. It's well supported experimentally. Doesn't mean that it's possible we could discover something that meant we had to change a little bit. Maybe the speed of light isn't constant over the time of the universe or things like that. And every once in a while in the news you'll hear something about some experiment that says, maybe something travels faster than the speed of light. These experiments are so subtle, though, that often there are confounding factors that you have to take care of and take into account. And it's very difficult at the precision involved to really see if something is going on or not. And so far, every time, Einstein, in a sense, the theory has been proven correct. Okay, so that's the twin paradox, most famous paradox of all, and just some of the analyses we've done in various ways with it, and then just the experimental results that show, yes, no matter how weird it seems, the twin paradox actually is an experimentally proven fact. Okay, for the summary this week, week 7, let's review the 3 major paradoxes that we analyzed. We won't, of course, reproduce all the analysis we did, but try to summarize the key concepts here to get the bigger picture view so we don't get lost in some of the details. So the pole and the barn paradox, remember the idea here was that we had Bob and Alice. Bob had the barn, Alice had the pole. Alice was running at a high velocity, 10-meter pole. Bob's barn, measured by Bob, is only 8 meters. But if Alice is going at a high enough velocity, then Bob sees the pole being length contracted and says, hey, no problem, the pole will fit in my barn. I can close the doors or take photos to show that at that given instant, the complete pole is within the barn. And so he says, hey, go ahead and try it, Alice. And Alice, meanwhile, is saying, my pole I can see is 10 meters long here. I've measured it. But she sees the barn being length contracted from 8 meters down to even a lower figure, and therefore she says, no way the pole is going to fit in the barn. And in our analysis, the conclusion was they're both correct. And the reason they're both correct is due to the relativity of simultaneity. In other words, that when Bob takes those photographs showing both ends are at one barn door and the other barn door, Alice sees Bob's clocks not being synchronized. And so when the rear barn door takes a photo of the front of the pole as the pole gets there, in Alice's frame of reference, her pole is still sticking out the other end of the barn because Bob's clock here has not actually taken the photograph yet. His clocks are unsynchronized. And so we did that analysis and showed that, yes, in one sense, Bob is correct. In his frame of reference, the pole definitely fits in the barn, and Alice is correct as well. In her frame of reference, the pole definitely does not fit in the barn, and the reason is that to Bob, his clocks are synchronized. To Alice, Bob's clocks are not synchronized. And then the spaceships on a rope paradox. Remember, the idea here was we had a stationary observer, two spaceships, rope between them, stretched taut, and to a stationary observer in between them would set them off on a sort of automatic acceleration such that the distance between the spaceships would always be constant to that stationary observer. And then the question was, what happens to the rope? Does it break or not? It would seem like if that distance is always constant, it shouldn't break. But the analysis shows, from the stationary observer's point of view, the rope has to break because it's undergoing length contraction. And if the spaceships remain at a constant distance, the rope cannot stretch that far anymore. So at a certain point, it will break. And then to the spaceship observers, though, they say the rope is going to break because the spaceship in front, to maintain the constant distance to the stationary observer, the one in front has to accelerate first before the one in back does. Again, it goes back to the relativity of synchronization, the relativity of simultaneity to do the analysis here. And so if the one in front, from the spaceship perspective, from their frame of reference, if it accelerates first, then it's going to stretch the rope and break it. So they do not see the spaceships accelerating at the same time, whereas the stationary observer does. And then finally the twin paradox, of course. Both twins or participants, we had Alice and Bob, observe the traveler return from the trip having aged less than the one who stayed at home, even though both of them, remember the paradox comes from, part of the paradox comes from the fact both of them see the other's clocks running slower than theirs. And so then how can that be? How can Alice observe Bob's clock running more slowly, and Bob observes Alice's clocks observe them running more slowly than his, and yet you get this asymmetry in the aging. As when Alice comes back, in this case, we had Alice do the traveling and come back. And also why is it asymmetrical? Because it would seem like from Alice's perspective, she sees Bob go back the other way and then return. So we spent some time trying to understand that asymmetry. It comes from the fact that there is some deceleration and acceleration involved for Alice or whoever is doing the traveling. And because of that, the key point was there's a change in reference frames by the traveler. And that accounted for the difference in times at the end, so that Bob, in this case, who stayed home, aged 10 years in our example, and Alice aged only 8 years. So that's a brief summary of the key concepts and key points that we've went through with these paradoxes. And next week we'll continue on. We're going to do a little bit more with actually sort of in the spirit of the twin paradox here. We're going to do a little bit more with time travel and also get into some of the other interesting things with the special theory of relativity in terms of how it was received, and even talking about a little bit about the general theory of relativity and the concepts of time dilation within a gravitational field and a few other things as well.